Hey guys, how are you? Have you ever encountered yourself in this scenario where you're like playing video games with really prominent audio effects like background music and stuff? Yeah? Okay, that's pretty cool. Yeah, me too. But have you ever wondered if the music actually helps? Because I'm sure it does in many cases. Like, imagine playing Just Dance without the actual music. But what about in games where you don't really need it? Like in Geometry Dash, for example, where the music is such a major factor of the game, but like you don't really need it. Or in what games do I know? Snake. Yeah, sure. That's a good example as well. Now, you could try just playing a game without music and with music and then see how well you did before and after. But you can't really make sound conclusions from doing this. Why? It's because there are other elements of randomness. Like, you might accidentally make a mistake at the very beginning because of a fly or like blink or something, I don't know. But the point is, you need more than one game to make sound conclusions. You need a large sample size. Once you have a large sample size, we can use statistics to mathematically model our performance and then make accurate predictions that we can trust. But there's more stats than the math. Once you have a question, you have to work on collecting a large enough sample. Wait, a sample? Basically, a sample is a set of data that you collect from the population. For example, if you want to know how good the MCU Disney Plus series are, instead of watching all like 14 of them, you can get a sample of one or two and then realize that they're painfully mid. Anyways, after collecting your sample, you need to validate your data, run your math, and then interpret your conclusions. It's a large process, so let's do it. Today, the question we want to answer is, does the audio of a video game actually help? The first thing we want to do is to make our question more specific. What exactly do we want to measure? Well, maybe one thing we can do is measure the difference in performance, whether that be the score, time survived, percentage of level complete, whatever. So we can rewrite the question as, is there a statistically significant difference in video game performance when using audio and performance when not? This gives us something that we can model mathematically, a numerical difference. For example, if without audio, I am consistently able to complete about 50% of the level, and with audio, I consistently complete about 55%, I would see a measurable difference of about 5%, which proves that I do better with audio. Now, we have to figure out how to collect the data. And so before we do this, we need to ask a few questions. 1. What video games will I use for this? We need games that have audio as a significant part of the game, but do not rely on it. For this study, I'll be using two games, Geometry Dash and Snake. Both have audio elements, Geometry Dash having background music, and Snake having audio feedback when moving the snake and eating apples and whatnot. 2. How do I collect the data without being biased? It's because I want to plan to do this in one sitting to save on time. However, by doing this, we may introduce a lurking variable, amount of practice. For example, if I play Geometry Dash without music for, say, 30 attempts, and then I play it with music for 30 more attempts, we may accidentally get results favored towards with music, not because of the musical element itself, but because of the practice and getting used to the level element during our first 30 attempts without music. So, to solve this, maybe one thing we can do is flip a coin, and then if it lands on heads, play a game with music, and then if it lands on tails, play a game without music. Thus, both settings have approximately the same level of practice. And then we continue doing this until both modes have at least 30 attempts to guarantee that we have enough data. And then 3, how do we measure performance? For Geometry Dash, we can do this by measuring the percentage of the level complete. And then for Snake, we can measure the number of apples eaten. Sounds good, right? And then finally, 4, what is the setting of the data? How can we describe the conditions we are collecting our data in a more specific way? Okay, so for Geometry Dash, I wanted to choose a level where I was decent in. So, not like Club Step, where I'm at like 9%, but not too good, where I could consistently win. That would mean my data is practically useless because in both cases, I would probably get like 100%. So, Stereo Madness is a good example of a data set that's too easy for me to use. For me, I chose Time Machine as I did decently, because my record before the time of this recording was about 72%. And there were no really frustrating bottlenecks I needed to worry about affecting the study. Looking at use cycles and your stupid upside down rocket thing. For Snake, I wanted to do this a little faster, so I chose the shortest map size and 5 apples to grow the fastest, lose the earliest, and overall finish the study in a shorter amount of time. Okay, so let's get started. So let's do this. Note to editor, which is myself. Insert montage here, by the way, remove. Now that we have the data, we need to figure out how we will use it to come up with our conclusion. We have two separate data sets, one for playing Snake and one for playing Geometry Dash, and we should probably run a test individually as their metrics are different. So this idea of splitting up results for different sections in an experiment is called blocking. And so now that we have this data, as mentioned before, how could we make conclusions? So the way we do it in stats is to come up with hypotheses and prove the validity of them. So from our question, we can make two different hypotheses that answer it. If you don't remember our question, it's, is there a statistically significant difference in video game performance when using audio and video game performance when not? So the first hypothesis we make is called the null hypothesis. This is kind of like the cynical theory, that there's no difference between average video game performance with and without audio, or that the difference between averages is around zero. Our second is the alternative hypothesis. This is a little bit more optimistic, that there is a difference between them, and that that difference is greater than zero, which is kind of self-explanatory, but whatever. We want to see if we have enough evidence to reject the null hypothesis. Can we prove that there's a difference enough to dissuade claims that there isn't? The way we do this is by assuming, first, that the null hypothesis is true, and then seeing how likely it is to get an observed difference as large as we observed. And then if it's not likely to get that much of a difference, we reject the null hypothesis. If it is, we don't say that the null hypothesis is true or that we accept the null hypothesis. We just say that we fail to reject it. If that sounds confusing, it's kind of like trying to figure out if aliens are real. For example, little bro here is sticking with the null hypothesis that aliens aren't real, and then when making observations, suddenly sees an alien in broad daylight. That's a substantial amount of evidence, and it's very unlikely for aliens to both not be real and then also see a little literal alien. Like, that's not possible. So because of that evidence, little bro rejects the null hypothesis and has significant support that aliens are real. On the other hand, if we didn't have enough evidence, we wouldn't really say that aliens aren't real. We may just need more evidence. So we would say that for now, we can't really prove they are real yet. Okay, so I heard the word likeliness a lot, you might be saying. How do we determine likeliness in statistics? To introduce this concept, we can use a sampling distribution. Let's start off with something called the normal distribution, which is otherwise known as a bell curve. This curve assumes that most of the time we collect a sample, we get results close to our true average, but they may deviate by little. So if our true average score in Snake is 40 apples, if we collect many different samples like before and then get their respective averages, we probably will get sample averages close to 40, like 35, 41, and 43, and we're less likely to get sample averages like 1, 100, 10, which are all very far away from our true average, which is 40. But before we run our tests, I'll make one small clarification. Instead of using the normal distribution, a better one to use is a t-distribution, which has slightly fatter tails. It's generally better to use this distribution, and I'll put some info why in the comments, but for now, assume that they basically serve the same purpose. We will be running a two-sample t-test for difference of means to figure out our hypotheses. So let's break down what this means. For one, we are trying to prove the significance of the difference in average or mean performance between two different scenarios, with music and without. And to represent our sampling distribution, we will be using the t-distribution. All right, so can we start? No! Before we even consider what we need from this test, we need to check if we're eligible to run it. In statistics, we have to check if our scenario matches before we run a specific kind of test. Otherwise, our results will be useless as we're not even sure if it's appropriate to use it. To do this, let's check our conditions. Our first condition is to check if the data we collect will be a random sample of our population. That is the data I will collect representative of what I actually do? We can assume that the way we are playing Snake is representative sort of how we play Snake with the specific settings, in that we use the smallest map, 5 apples, and kind of normal speed. As if we play with these conditions, there aren't too many differences from our study. The same is the case for Geometry Dash, at least for the level Time Machine. I'll just be playing how I normally do, except I'll be recording my results, which is not really a big deal in my opinion. Next, we need to ensure that our sample is less than 10% of the population. This assures that our sampling method is quasi-independent. In our case, of course, I have played and will play Geometry Dash and Snake thousands more times, so I can say that our sample satisfies this condition. Next is the independent groups condition. This just verifies that there's no relationship between the two groups, music and no music. One does not influence the other, is what this condition tries to satisfy. This is satisfied because I choose randomly the order at which I sample these values. This condition would be violated if we, as mentioned before, ran 30 attempts with music and then after that 30 attempts without, because of potential practice that could have been gained during the music that carried on to the without music attempts. Because we do not do this and flip a coin every time to choose which one to play, we satisfy this condition as well. Now before I get to the final one, there's a reason why I ensured that I had at least 30 data points for each case when I discussed how I collected the data. So you can run this two-sample t-test, and it is actually designed to run when we have less than 30 data points. However, in those cases, we have to guarantee that our original sample data is symmetric and unimodal, which I don't exactly know about. So I'm ensuring at least 30 points to not worry about this. This is the nearly normal condition. Can we start on? No! What do we need when running this test? While I won't go over the mathematics behind this and will demonstrate how to use a calculator, or in this case code, to solve this, it's important to know what you need for this test. For each scenario, with music and without, you need the mean and standard deviation. The mean tells the average performance you did with that category. So, if for example, you got an average score of 40 apples, we would say that your mean is 40. The standard deviation gives you an overview on the variation of performance in that category. So for example, if your results were chaotic, like you sometimes did good or bad or whatever, you'd have a large standard deviation. However, if your results were relatively consistent, you would have a smaller one. In simple terms, what the test tries to do is that we first assume that the difference between average performance is 0, and then we use our two standard deviations, the ones with music and then the ones without, to figure out how varied we should expect our results to be if the average performance is 0. And then we use the difference between our two means to see how expected it would be to encounter such a difference. We represent this by something called the p-value. That is, the probability of observing a result as extreme as observed or greater given that the null hypothesis is true. Now, let's run our test. Snake. The first thing you want to do before statistical testing is to get an overview about your data. To do this, I created a histogram of the distribution of scores with and without music. This is how it looks like. Both distributions appear relatively unimodal and there are no significant outliers. And just visually, it seems like there isn't really a difference, but what's interesting to me is that with music scores tend to be more extreme. That is, I tend to get more extreme highs and more extreme lows, so on average my score is about the same. After this, you want to get your summary statistics. This is what I got. I played the game 36 times without music and 30 times with music. And the mean score with music is 46 apples, while the mean score without music is 42.2 apples. Now, just by looking at this, that's 3.8 apples. That seems like a big difference. But this is where the standard deviation comes into play. For our standard deviations, music scores on average are within 19 points from the mean. Without music, scores are within 12 points of the means. If we make distributions modeling this, we can see that there's a relatively significant overlap, so it's not clear per se that there's a difference yet. Then, we conduct the test. As mentioned, we are doing a two-sample t-test for difference in means. I will not go over too much how this test works in this video, but I'll put some information in the comments. However, I would like you to know how to use this test, whether it be in coding or on the calculator. In this case, I am using code to run this test, however, these skills are very transferable to the calculator. I am using scipy.stats, a popular statistical modeling library, to run our test. First, you want to separate out your data into two groups, the one with music and then the one without, in our case. Then, you pass that value into the function t-test-ind from scipy.stats that'll calculate the summary statistics that we came up with above, mean, standard deviation, and count, and then use these statistics for our test. Even though it already does this work for you, it's a good practice to get these values beforehand, like we just did, to understand your data better. This function will return two values, your t-statistic and your p-value. As mentioned, the p-value is the probability of observing results as or more extreme as observed if our null hypothesis is true. In our case, the probability of observing a difference in scores as or more extreme as 3.8 apples in our sample if, in reality, there's no difference in scores. If this probability is low, we can assume that it is so unlikely that it is probable that there actually is a difference in our scores. The t-statistic is used to calculate the p-value, and it's basically a measure of how extreme our observation is. Remember how our p-value checks the probability of observing results as or more extreme as observed, and we use this t-statistic to determine this. But wait a second, don't we just use the raw difference in scores to get our p-value? Why can't we use the raw difference in apples as a measure of how extreme something is? Great question. In this case, we basically do. The t-statistic is derived by taking this raw difference and then standardizing it based on our standard deviations. Why do we do this? Because, for example, if we have a difference in 3 apples, but our scores are very tightly packed, that is more meaningful than if we have that difference and our score is all over the place, or like more spread out. It's just more likely to observe said difference if our scores are more random. So, what did we get? We got a t-statistic of 0.95 and a p-value of 0.344. This means that if, in reality, there's no difference in scores with and without music, we can expect to observe a difference of 3.8 or greater 34.4% of the time. How would you interpret this? For me, this is not enough to indicate that there is a difference. 34% is relatively common odds. It's about the same probability of rolling a die and getting 1 or 2. Because it's not so shocking to get such a difference, we fail to reject the null hypothesis, that there's no difference in scores when using music or without, and we need more evidence if we want to see potential evidence of a difference. So my conclusion, for Snake, music doesn't really matter. Geometry Dash. For Geometry Dash, we basically follow the same process. Let's have a look at our histogram. We see that this time, the data is not unimodal. There are several different peaks. Can you figure out why? Feel free to pause for a minute and put something in the comments before I resume. Okay, I hope you did that. The reason is that in Geometry Dash, there are a few areas that I tended to struggle with. In the histogram, we see that I often lost in the very beginning, at the 0 to 20% mark, middle, 40 to 50% mark, and ending, 60 to 90% mark. There are gaps in between those areas which were the easy parts where I didn't really lose. We also can visually see some difference between the music and non-music attempts. It seems like without music, we fail a little more at the beginning, and with music, we tend to reach the end a little bit more often. So, maybe slightly better with music than without. But can we corroborate this with statistics? Before we do the test, let's have a look at our summary stats like before. So, we played Geometry Dash with music 30 times and without music 30 times as well, just enough to satisfy our nearly normal condition. When playing with music, I went through on average 57.9% of the levels successfully. Without music, about 38.7. Already, this seems like a larger difference, 19.2%. But we also need to look at the standard deviation. For our standard deviation, my score varied for music by about 31.9% on average. So another way of interpreting the standard deviation is by saying that on average, my score was between 31.9 from our mean, so between 26% and 89.8%. And without music, my score varied by about 31.44% on average, meaning my score on average was between 7.26 and 70.14%, which is 31.44% of the mean. Now let's see if this results in any statistically significant difference. After separating our data into two groups and passing it to t-test IND, we get a t-statistic of 2.35 and a p-value of 0.022. Now this is interesting. This means that if there really was no difference between playing with and without music, we should expect to see a difference of 19.2% or greater only about 2.2% of the time. This is a lot less likely to occur. Whereas our snake example had about a 1 in 3 chance of occurring, this is about 1 in 50. That is much harder to achieve and also below the typical threshold, 5%, used in most studies for statistical significance. Because of this, we can reject the null hypothesis that there's no difference in scores when using music or without, and provide significant support that there is a difference in scores between the two cases. So my conclusion for Geometry Dash, drum roll, music helps. Conclusions and caveats. So basically, what did we learn from this? Well, we learned that whether music matters depends on the type of game. In our case, Snake didn't really have a difference with audio elements or without. However, we noticed a strong difference when playing Geometry Dash. This means that music has the potential to improve player experience significantly, though it probably won't always do that. However, there are some important caveats to consider before taking these conclusions for granted. We played both under very specific conditions. Snake with 5 apples in the smallest map, and Geometry Dash with the level Time Machine. We are assuming in practicality that these conditions would apply to other situations. However, we cannot apply it as a fact, and we would have to run studies on other cases as well before we can absolutely be sure. But, assuming that they do apply, we have successfully used statistics to mathematically demonstrate the ability of music to help player experience. We can improve our results by running more varied conditions. For example, using more levels in Geometry Dash or exploring different settings in Snake. We can also have more people in the study or try playing other games. For example, Tetris or Mario. I hope this video helped you get an introduction into statistics. Please like and subscribe and have a great day. It would mean a lot to me, and also do it for Blob. Blob is the name Blob. Yeah, okay. Mr. Blob. Have a great